But as we go on this semester, you'll begin to appreciate why everything we arrive at, beginning tonight, all the final equations we arrive at, will be useful, and you will see that, okay? So what is an Ar1 model? So we're going to use the simplest Ar1 model, the simplest one. Let's back up. Remember, I told you last time that an AR autoregressive model, especially an Ar1 model, look at this equation 2.8. Can you see this? Mainly, can you see this?
Yeah.
Okay, excellent. So this is a simple autoregressive model. It is, why do we call it a linear model? Because this is X. So you can think of this as return to Facebook at time today, okay? So xt is equal to a constant, a constant plus another constant times return to Facebook, yesterday's return to Facebook, plus some error. So in other words, Facebook's return today, we show, or we know somehow that is determined by a given constant, an average return. So the return to Facebook today is some average number plus a function of yesterday's return, Facebook's return, plus or minus something. So this is what we call an error term. In OLS, in Echo 4000, we just call this epsilon, and we say it averages out. The expected value is 0, the variance is homoscedastic, and so on and so forth. The same way here in time series, okay? For time series, we simply call this what did we call this again? What do we call this? What kind of error?
White noise.
We give this error term a name called white noise. And the properties of the white noise are just like the properties similar to the properties of the error term in Echo 4000. The average is 0, so the expected value is 0. The variance is constant, is homoscedastic. The covariance between return today and return yesterday and return 2 days ago, return 2 days ago and return 3 days ago. The covariance between returns separated by any lag 1, lag 2, lag 3, lag 4, is all 0. We have discussed that in the past. So this white noise has very nice properties, okay? Simple properties: average 0, constant variance, auto covariances, and therefore auto correlation at every lag equal to 0. And it doesn't have to be a zero mean white noise. It can be a constant mean white noise. So in that case, the xt would be equal to some mean value plus the white noise. If the mean value is 0, then we call it a zero mean white noise. If the white noise comes from a normal distribution with IID observations, then we call it a Gaussian, G-A-U-S-S-I-A-N. Okay, that's Gauss is responsible for the normal distribution. So we call it a Gaussian white noise. So it's a very simple process. So, but then what is the autoregressive model? An autoregressive model is we take this part, or these two parts, we take these two parts, which is linear in the previous return term, and simply add it to the white noise. So the simplest time series model is xt equal to white noise. That's a very simple, that's the simplest, okay? So on Thursday, I'm going to ask you to go get data and show me that data and prove whether it's white noise or not. We've seen how this worked. We saw that last weekend and a few classes ago. But so if I can ask you, go grab IBM returns for 10 years, day by day or month by month, and determine whether it's white noise or not. If it is white noise, then that means we're saying the returns of IBM every day is equal to A sub T, that's all. So if IBM's return over 10 years, day by day, are white noise, it's a white noise process, then we say the returns, this one, this left-hand side is equal to nothing, nothing, nothing plus A. So XT will be equal to A. So the XT is equal to a white noise process. Is a white noise process. We already said the mean of the white noise process can be constant or can be zero. In this case, in this equation 2.8, the mean of this white noise is equal to 0. It doesn't have a constant attached to it, okay? By assumption. Here, look at that. Where the series A, the white noise process, is assumed to be a white noise series with mean 0 and homoscedastic, constant variance. But when we add this term to it, when we add a term that is linear in the previous return, so we're saying now that today's return is given by a constant plus yesterday's return times a given number plus white noise. Once we add these first two terms, then this whole equation 2.8, we call it an autoregressive model. But because we're saying today's return is determined by yesterday's return only, plus white noise and a constant, we call this an autoregressive model of order 1, because we're only interested in lag 1. We are saying tomorrow's return will be determined by today's return. Today's return is determined by yesterday's return, only one time period in the past. For an AR2 model, AR2 will be xt equals this constant plus this constant times xt minus 1 plus constant 2, so phi 2 times xt minus 2 plus a. Okay, so if you look, let's see, I think it's up there. Let's see. I look at so many books, so sometimes it's difficult to determine what page. I think it's further down. Let's see.
I think you passed it, Professor.
I'm looking for an ARP.
Yeah, it was up. It was up there.
Okay, it was up there. Okay.
Right here. Oh.
Where, up?
No.
Down?
No. If you go one more, a little bit, 2.9. The 2.
Oh, 2.9. Down, down, down?
No, up.
Up.
This
okay.
page, just scroll once.
A little bit.
Yeah,
right
right
there.
here.
Right there. Okay. Thank you so much. Okay. So an ARP is xt equal to the constant plus lag 1 factor plus lag p. So if I'm saying that today's return is determined by all the past returns up to 10 days ago, all the daily returns up to 10 days ago, then that's an AR10 model plus white noise, of course, okay? So of course, the problem is always, if you and I go download Facebook's day-by-day return for the past 20 years, and we determine that it's an AR, it's an autoregressive time series. That is, every day's return is determined by past series of returns. But how many lags in the past? That's a crucial question. It's not only enough for us to say it's an autoregressive model, AR model, but up to what lag? How far back do we go for the returns that far back to determine today's return? So one of the things that we always like to know is the time series, those returns for Facebook, are they autoregressive? If they are, autoregressive of what order? Okay, so the properties we are going to be determining today will help us greatly to see whether, to help us determine the lag visually. And the trick, as you will see, will be in examining, in looking at the ACF, autocorrelation function. So when we eyeball the ACF, then we can suspect maybe this is an AR4, AR3, or AR10, okay? Again, but just like for white noise, we did for white noise. Remember, for a white noise series, we said the autocorrelation at each lag should be 0. But sometimes we draw the autocorrelation function and we see that each autocorrelation is not really 0, but they all fall within the plus or minus. You remember the confidence bound? Once they all fall inside, then we can say statistically at the 5% level of significance, they are, statistically not significantly different from 0. In other words, they are 0 statistically. The same way for an AR, from autoregressive model. We're going to draw the ACF, and then given what you and I will prove as to what the autocorrelation at each lag will be, we're going to find an equation that will tell us what the autocorrelation at every lag will be. Using that, and then using our confidence bound, plus or minus, up and down, the dashed line, then we can determine whether it's an AR model or not. And if it's an AR model, what lag? AR1 or AR2 or AR3? But that would be visual. Because remember, for white noise, after looking at the autocorrelation function, we then went on and we did the portmanteau test to see if they are together all 0. Okay, so the same way for autoregressive model, we are going to look at it visually, and then we are going to apply a statistical test. 2 ways. Okay, so tonight what we want to do is here. So if you look at this page now, properties of autoregressive models. For effective use of AR models, to be able, you and I to be able to work with them effectively, it is useful to study their basic properties. Okay, so in this textbook, they discuss the properties of AR1 and AR2 models, but we're going to today begin by studying the properties of AR1 model. And what are the properties we're going to study? We're going to say for a given AR model, for tonight we're going to study AR1. For a given AR1 model, what is its mean? We're going to show what its mean has to be for stationarity, for the AR model to be stationary. So tonight we're going to work on the mean, only the mean of an AR1 model. Then on Thursday, hopefully after discussing homework and everything, then I will begin to show what will be the variance, and then what will be the autocovariance, and then autocorrelation at every lag. And then, so we're going to find one equation that you can, given all the parameters, like the phi 0 and phi 1 and phi 2 and all that, you can plug those in to that one equation to find what the autocovariance and therefore autocorrelation will be at every lag. William Morris, you have your hand raised.
Yeah, Professor. So the mean and the variance of the white noise model is is different than the mean and the variance that we're going to get?
Of course. But are you surprised?
Well, I figure since we're all we're doing is adding variables with the white noise model, I thought it
Exactly.
wouldn't change much.
But yeah, but look here, look at equation 2.8. Yes.
Hmm.
The mean, what is the mean of this white noise process? We have been given where the A process is assumed to be white noise with mean 0. So this is mean 0, right?
Hmm.
So the mean of this, the mean of XT, you can think of XT as daily returns to Facebook, or weekly returns, or whatever T is, okay, or monthly returns. So the mean of this, the average of this will depend on the average of these two things. Is that correct? Yes, yes, yes. William, you have to tell me yes.
Yes.
Because the mean of this A is 0, right?
Right.
So the mean of this XT has to be the mean of all these three things, yes?
Yeah.
Since this one is 0 already, since the mean of this one is 0, therefore the mean of XT has to be equal to the mean of this and the mean of this. Are you with me?
Okay.
Thank you, William. I didn't talk to you before class, did I?
No.
No, so I never paid you to ask me this question. But that's I'm serious, that's a fantastic question you just asked me, because it's now going to lead me to what I want to do tonight. Okay, so
Perfect.
fantastic. Thank you, William. So yes, remind me. Okay. Roxolana, I still haven't heard from you. I know very soon. Okay. So here, look. So the mean, so this is the AR1. Why is it AR1? Because we have only one lagged return, right? On the right-hand side. We're going to look for the mean of this tonight, the expected value. And then on Thursday, we shall look at the variance, and then look at the covariance, the autocovariance, and therefore autocorrelation at every lag. And then we are able to draw the ACF, autocorrelation function. Okay, but tonight only we're going to look at the expected value of XT. Expected value is the first moment, yes? Is the first moment, which is the mean. But we already know, thank you, William, that the mean of A is 0. Therefore, the mean of XT has to be 0 plus the mean of each of these. That's where we're going. And let me give you the answer up front, in case the world blows up before we finish it, okay? Look at this equation here. Look at this. Everybody sees this? So the mean, so in other words, the mean of XT, which we call the mu, is equal to the constant plus this constant times mu, or the mean of XT is equal to this, which is equal to this. So tonight we're going to derive this equation here. Everybody see this equation I'm circling? We're going to say the mean of the Ar1 process is equal to the constant, okay, phase 0 divided by 1 minus the coefficient of the lagged return. Are you with me so far? Everybody seeing this?
Yes.
Yes.
So this is exactly what we are going to determine today. And as you will see, the mean for AR2 will be this thing on top divided by 1 minus phi1, which is the coefficient of the xt minus 1, minus phi2, which will be the coefficient of the lag2 return. But let's begin with a very simple one, okay? Now, unfortunately, the proof I'm going to show you today, I am not using phi0 and phi1. I am using mu here. I'm using mu here and phi1, because that is, in the traditional literature, that is what is used, okay? All right. Now, please, everybody, can you go to Blackboard now? If you go to Blackboard, I put, I uploaded I uploaded three files. I call them AR1, page 1, page 2, page 3. Okay, I wrote them by hand last year, And rather than just go through the textbook, I said, let me go through with you every little step of the proof, okay? If you see every little step of the proof, I think you'll become a little bit more confident in this. So I am going to stop sharing now. So everybody, this is what we are going to show tonight. And I have 3 pages that I uploaded to Blackboard. So if you want to go to your Blackboard account and pull those 3 pages, and please tell me if you see them.
Yes, they're there.
Okay, good. So now I'm going to share them. I'm going to share mine here. So you can look at yours and take notes while I share mine. Before the class, I was playing Jamaican music. So if you hear Jamaican music in the background, don't be surprised, okay? But I kind of put it on pause until after class. I'll begin to do it. Do you see this? No, yeah, you don't. You see this. Okay. Again, it is my handwritten. Sometimes I just write for myself, okay? I sometimes I put my, because if you and I were in a classroom, I'll be writing all of this on the board in the classroom at Baruch. But you know, last year I was writing this up and I said, you know, why not share it with my students? So please, I hope you don't mind my scratchy handwriting. It's horrible anyway.
I think it's pretty neat. But I don't know.
No, it's not neat. Thank you. You're trying to be nice to me.
You did a great job, Professor.
Thank you. But I thought you guys might like to have this because I go through every single step of the proof, okay? So for those of you who are new to this, many of you probably do not need this step by step. Wait, did I just lose you now? I lost you guys. Okay. Okay, so you can follow me with this. Now, so please just follow me step by step, okay? So this is what we call the unconditional mean, and I'll explain that later. Let's not, so I'll make a big deal with the difference between unconditional mean and conditional mean, but not tonight. What we are trying to find is the mean of this process unconditionally. Don't worry about the word for now. Look, you see, this is different from the one in your textbook. The one in your textbook uses x of t, okay? Return to Facebook, day by day, return to Facebook. But I'm using phi, instead of phi 0 and phi 1, I'm using mu and phi 1, okay? And then this is not mu, this is u, error, okay? This is a white noise error. In your textbook, this is what is called A in your textbook, okay? But again, I was just playing with this myself, and I'm using the notation that I learned when I was learning time series. This is more general, but I think I prefer your textbook because it's using the same phi 0. It's like alpha 0 plus alpha 1 xt minus 1. So, okay, but I hope you guys can keep track of this, all right? So guys, look, if this thing here, are you looking at it, this mu? If this mu, if we set it to 0, then this would be a 0 mean Ar1 process. Are you following me? Yes?
Yeah.
Okay. So if we put this to be 0, then this would be a 0 mean Ar1 process. Why is this an Ar1 process? Because the return at time t is determined by a white noise error plus the return at time t minus 1. Okay. By the way, this is t minus 1, so sorry about that. Okay, so we're trying to find the first moment. The first moment is the expected return, So the expected return of this must be the expected return of everything here, okay? Everyone, just keep with me. I'm just going to run through this. If I lose you at any step, stop me. But before this class ends, I want to run through all the 3 pages, okay? So I'm just going to keep talking. If I lose you completely, stop me and I'll repeat that line, okay? whatever you do to this left-hand side, you have to do to the right-hand side. If you take average of this left-hand side, you must take average of the whole right-hand side. So the average, so the expected value of this is equal to the expected value of everything on the right-hand side. And then you break it up. So expectation of all of this, statistically, you can break it up. It's equal to expected value of this plus expected value of this plus expected value of the white noise. Okay. What is the average of a constant? If I have constant return for 5 days, everybody return for 5 days, Monday through Friday for IBM is 7%, 7%, 7%, 7%, 7%. What is the average return?
It's a constant itself.
Yes. So the expected value of the constant is equal to the constant. The expected value of a constant times a variable is that constant times the expected value of that variable, okay? And the expected value of the white noise error term is what?
0.
Is it 0?
It's 0. It's given. Okay? This is a zero mean. This is a zero mean white noise. We saw that in the textbook. Remember? Okay.
Yes.
So that means the expected value of this, of the time t return or process, is that same constant plus the phi, the coefficient, times the expected value of the lagged return, the 1 period lag return, plus 0. Therefore, this, the expected value is equal to mu plus this. Okay? It's in your textbook.
I have a question.
Give me a second. If you look at your textbook on page 52, it's right there. Okay, so it's on page. So you can write page 52 next to this. Or yes, ma'am. Who is that?
It's Roxalana. Hi.
Now I can die in peace. I've heard from Roxalana. Almost die in peace. I need to hear from Lilith too with question.
Okay.
Yes.
So you said that this is a zero mean Ar1 process, correct?
No.
No?
It would be a zero mean Ar1 process if this constant is 0.
Oh, okay. So why did you make the white noise 0 again? Can you please repeat that?
We made the white noise 0 because look, if this white noise has a mean, it would be A plus this white noise. But the A and this A will bound together, and we can so it's not, it will just make our equation a little bit complicated, okay? This is just for convenience that we're choosing this to be a zero mean white noise. We want the white noise to be as simple as possible.
Oh, okay. Thank you.
Okay, but it is by assumption. Are you with me?
Yeah, but why is it an assumption? Like, why can't we make it some other number?
It's just like I'm saying, look, you know, I'm assuming my student is Russian. You know, that's where I want to begin. I can say I'm assuming my student is Russian and American and Indian together. That's a complicated human being, right?
Yeah.
Yeah, but I just want to simplify my life. Because look, if I introduce a constant here, instead of just this u, it will be constant plus u. And I have to keep track of a constant as we go on and on and on. It's messy.
Okay, so what does that first star represent? Is that just...
Which one? This one?
Yes.
This tells me that the average of an Ar1 process, the expected value, which is the first moment, remember?
Oh, okay.
The first moment or the average of an Ar1 process is equal to a constant plus this times the average value of yesterday's return. So in other words, if Roxana, if you and I are interested in studying, if we go collect data, day by day data for 20 years for Facebook, are you with me?
Yeah.
And Facebook follows an Ar1 process. Then we're Ar1 process with zero mean white noise. Then we're saying we can say off the bat that the average of all that series is equal to the constant plus this constant times yesterday's return at every day,
Okay,
at,
thank
at
you.
every time period in the process. Okay.
Without white noise. And this is
Yes. Yes,
okay.
without white noise, yeah, because white noise has averaged out.
Okay, sounds good.
It's like in Echo 4000. Remember, your residuals, we assume, have zero average. The error, the expected value of the error is zero. That's one of the assumptions of OLS. I'm sure you remember this. Okay. Okay, everybody. So we are saying that for an AR1 process with zero mean white noise and a constant, that the average of that white noise process, if you add up all those, Roxolana, if we add up all those daily returns for Facebook, day by day by day by day by day for 20 years, and we average them, that this is the equation that will give us the average. Now, if this is a zero mean AR1 process, Roxolana and everybody, then this thing here will be zero. This term will be zero. Yes?
Yes.
Okay. And then the average will be just equal to this term. Okay?
Okay, sounds good. Thank you.
And you remember last Thursday, I showed you an example. Yes. Just everybody just hold on right now. Okay? I didn't want to do this, but because of Roxolana's question, thank you. There's something I'm looking for now. Actually, I think it's here. Oh, is it here? Okay. Okay, can you guys see this thing I'm showing now?
Yes.
Okay. What is the constant term here for this AR1 process? What is
Zero.
The constant term is zero. This is a zero mean white noise. What is phi1 here?
Negative 0.9.
Negative 0.9. So what is the average of this process? Here, we're saying the average is zero, and I'll show you why, okay? We're saying the mean is zero, and I'll show you why in a second, okay? But I just wanted to show you this process because here, Roxolana, that first term is equal to zero, okay? And the phi is equal to negative 0.9. I think I also showed you last week, there was another process I showed you. Here, you see another one. The phi is equal to plus 0.9 here.
Which means it's stationary, right?
Yes.
Okay.
That's great. All right. You kind of, all right, good. Okay, so let's go back to, okay, everybody. Is everybody with me? Please, if you are not with me, just speak up now because I'm moving on to something else and it's going to be quick. Okay. Now look. So now we have determined that this is the first moment. Everybody now look, see what, oh, you're not seeing this, are you? Okay, sorry.
We were looking at the book.
Yeah, you are looking at the book. Yes, sorry. I just noticed. You see, professors can read signals too. It tells me it's a yellow. Oh, sorry. Okay. So everybody looking at this, right? With stop, William. You see, this is 1 star, right? So this, everybody sees this. Now, see what I'm going to do. This is xt minus 1, right? Now look here. The AR1 process says x sub t, today's return, is equal to some average plus phi1 times yesterday's return. Now, if I want to write yesterday's return, like here, now, look at here, below, xt minus 1, yesterday's return obviously will be equal to the same average plus phi1 times return 2 days ago. Everybody follow me here?
Yes.
Plus white noise the previous day. Look at this equation and convince yourself. all you need to do is, oh my God, what did I just do? All you need to do is compare it with this one. XT is this. That means, you see this XT and UT, the error, they have the same time period. And then this one is lagged one time period between before these two. The same way, XT minus 1 is equal to UT minus 1, the error, the white noise. And this one has to be minus 2. You see that? Everybody follow me?
Yes, Professor.
Okay. Yes.
Really quickly. So does that mean that is AR2?
Yeah, no,
That's the AR2
no,
process?
this is an AR1 process.
It's still an AR1.
Yes, because
Okay.
look, because yesterday's return is explained by a return 2 days ago, just one period behind it.
One period. Okay.
And XT minus 4 is explained by XT minus 5, one period behind it. You understand?
Yes, Professor.
Yes, and AR2 would be XT equals yesterday's plus, in the same equation, 2 days ago.
Okay.
Okay. Who is this asking me a question? Your voice is kind of unique. Ah, Natalie, I must.
Yeah, I am Jamaican, so.
Yeah, oh my God. Just go away. You don't need to attend my class anymore, okay? You'll make an A already. Because I don't know how you guys began to make music that moves me so much. Anyway, for another day. All right, guys, see what I'm going to do now. I'm going to do some magic. I am going to remove this. Roxalana, are you with me?
Yes.
You see this equation that we arrived at before? I'm going to the trick is I'm going to substitute this thing out and put this. Okay? And then I'm going to, the process is called recursive. All right. Hold on. Because if you understand this, then my life becomes easier. It's a C-U-R-S-I-V-E, recursive process. Okay, everybody look, I typed it on chat. It's a recursive process. I go one time period behind, I get the equation, xt minus 2 is minus 1 is to the right-hand side. I remove that, I put xt minus 2, I remove that, then I put x3. So I'm going back in time and hopefully I get to the end. You see, we're beginning of time. And then I stretch out all those equations and I solve them, I substitute, and I get my answer. So what we are going to be doing is we are going to be backing up one lag, one day, backing up one day, until we get to time 0. Okay, guys? That's called a recursive process. It's a very neat trick in econometrics that we use to make proofs. Okay. All right. So I'm going to be quick now, okay? So please stay with me, everybody. So now I substitute this. Xt minus 1, because this is an AR1 process, must be equal to mu plus phi1 times xt minus 2 plus ut minus 1. Now, so I put this equation in this, and if I do it, oh gosh, I hate online classes like this because, I mean, I love it because I don't have to commute, but in terms of, I love to write this on the board and prove this for you on the board. Just stay with me. So therefore, now I go back here, I remove this xt minus 1 and I replace it by everything here. So this one now becomes, the first moment is equal to mu plus phi1, but instead of xt minus 1, I put all of this in. Okay? I put all of this in. Okay? I do not bother to remember, this is because this one, or the mean, cancels out, right? So all I need to do is just substitute for this. So I put everything here. Everybody look at this equation and tell me you understand this. Okay?
You expressed xt minus 1 with a lag of xt minus 2, and then you exchange it in the expected value of xt.
Exactly. So here, I just substitute this one out because I said this xt minus 1 is given by this, right? So,
Right.
so in this equation, I just I remove xt minus 1 and I replace everything here. You see that in equation 2? That's what I did. And then I expand it. So this is the same, but here I remove this parenthesis, right? This bracket. So it's phi1 e of mu plus phi1. Okay. What did I just do here?
You just did mu.
Yeah. No, I just brought the expectation inside. That's what I did. You see? So I brought the averaging inside. So I put this out here, and I bring this is expected of this here, expected of this here, and this one expected of this. So I move the averaging, the expectation, I moved it into the bracket. Everybody with me?
Yes.
Okay. And then on this next line, everybody, you told me that the average of a constant is the constant, right? 7, 7, 7, 7, 7, 7. Average of that is 7. And the average of a constant times a variable is the constant times the variable. So this is phi1 times this one, the same. And we know that this is a white noise process. Yes, everybody?
Yep.
What is the expected value of the
0.
white? Thank you. Thank you. It's like Anoche, move on. All right. So now we get to number 3. So number 1 was with this. Number 2, 2 stars was I substitute. Now we arrive at number 3 here, which says the expected value of xt is equal to the mean plus, I remove the bracket, this phi1 times mu plus phi1 times phi1 is phi1 squared times expectation of this. Everybody with me now?
Yes.
Guess what I'm going to do next? I'm going to remove this xt minus 2, express it in terms of xt minus 3. Yes? Sorry. Okay. Sorry. I was teaching French students today, early on Tuesdays and Thursdays. That's what I do. Sorry about that. All right. So now I'm going to bring up page 2. Everybody bring page 2. But look, but before you look at page 2, what am I going to do? This xt minus 2, can anybody tell me what xt minus 2 will be? Just like here. So xt minus 2 will be mu, will be this number plus
phi1 xt minus 3
xt minus
minus
3
2.
ut minus 2. Fantastic. Okay, so that's where we're going now. All right, so let's go to page 2 of this. I think you all have access to it already from Blackboard.
Yeah, we do.
Okay, so page 2. So let me make this a little bit bigger. This is the trick in econometrics, okay, the recursive process. It works in time series econometrics. So here, xt minus 2, again, is determined by xt minus 3 and u2 minus 2. The error term, the white noise term, and the left-hand side term, they're always contemporaneous, the same time period. And this one is lagged. And then what do? I go back to page 1, I substitute xt, this right-hand side for xt minus 2. So all of you can now look at the last page of page 1, the last line of page 1. So that is what I'm doing now. So I say xt is equal to mu plus phi1 mu plus phi1 squared. But instead of xt minus 2 now, I substitute everything here. Expected value of mu plus phi1 xt minus 3 plus phi u error, white noise error t minus 2. And again, I do my thing. This is the same. This is the same. Here, I move this expectation inside. Again, I'm just repeating the same step as I did earlier. I bring this expectation inside. Expected value of a constant is a constant. expected value of a constant times variable is that constant times expected value of the variable. Because this is a white noise process, ut minus 3 is 0. So what do? I expand this. So this is same plus phi1 squared mu, this one. Phi1 squared times phi1 is phi1 to the power 3 times et minus 3. Guess what I'm going to do next? I substitute for t minus 3. I do so xt minus 3 is mu plus phi1 xt minus 4 plus ut minus 3, and so on, and so on, and so forth. Yes?
Yes.
Okay. Now here comes the trick. So this is the money game now. This is money. It's like bank, you know, it's like time is 0-0 and you sink the basket in basketball. All right, so look, so if we keep repeating the process, if we keep going down, we'll arrive at something like this. That expected value of xt is equal to, look, mu1 plus, look here, up here, mu plus phi1 mu plus phi1 squared mu plus, you know, if you substitute this out, there'll be mu. So what can I do? I can just bring out this mu. Guys, if I remove this from here, I have 1 left. Yes?
Yes.
If I remove this from here, I have phi1 left. If I remove mu from here, I have phi1 squared left. I keep going. So mu to the parenthesis, I just substitute out, I pull mu out. So I have all these things. 1 plus phi1 plus phi to the power 2. But if you want to write this down, this is phi1 to the power 2. What is this? Phi1 to the power what?
1.
1. And what is this? Phi1 to the power?
0.
0. Exactly. So I can write mu parenthesis or bracket phi1 to the 0 plus phi1 to the 1 plus phi1 to the 2 plus phi1 to the n minus 1, because I am still continuing, plus phi1 to the power n times this one. Just like here, look, here, when our n was 3, we went this to 1 to 2 and then 3. So 2 was n minus 1. If my n is 3, then the last mu here will be n minus 1, 3 minus 1. So mu up to 3 minus 1, and then phi 3, phi n, expected value of xt minus n. Okay, so it's just like this equation here. I generalize. Guys, this stuff is easy, okay? It's just, we're just looking at using many symbols. But if you understood that first step on page 1, we're just repeating the same thing. Because we are repeating it going backward, we're having higher and higher exponent powers. Okay, so everybody, this here, if you're having a problem understanding this, back up here and then back up here. This is exactly like this. Okay, it's exactly like this. But instead of 3, I'm using n here because I have done it not 3, not 4, not 5. I've gone way back to n lags. Okay, so we have this general equation, okay? Now look at what I've written here. If we assume that this Ar1 process, why do I call this Ar1 process? Anybody? Why do I call this an Ar1 process?
Because you're using only 1 lag.
We're using
So
only
it's-
1 lag. At every time period, we're going back 1 lag. So it's an Ar1 process, okay? So if we assume that this is an AR1, that this AR1 process is stationary, for it to be stationary, this thing has to be, the size of this has to be less than 1. Who said that before? Was it Roxolana or Natalie? Somebody, when I showed you that example with 0.9 and minus 0.9, somebody told me, therefore it is stationary.
Yeah, I said that.
Who said that, Roxolana?
Yep.
Yeah, that's because this is the condition for stationarity, okay? Because if phi1 is exactly equal to 1, it's a non-stationary process, and we call that that specific one, we call it a random walk. We shall say it on a future date, okay? All right. So here, if we assume that the AR1 process is stationary, that is, if we assume that phi1, the size of phi1, not the sign, remember, what do these two lines mean?
Absolute value.
Absolute value. So we don't care whether it's negative or positive. We're just looking at the number itself, yes? If it's less than 1, look, then this thing to the n will tend towards 0 as n becomes very large. Everybody, let's go to page 3 and I'll show you what I mean, okay? Somebody answered we. Sorry. All right, so let's go to page 3. If you have page 3 already from Blackboard. Okay, so this is page, can you see? Yeah, you can see it. Okay, if that AR1, that AR1 time series is stationary, then phi1 is less than 1 in size, okay? Let us say phi1 is 0.9, okay? You guys with me?
Yes.
Okay. What is phi1 to the power of 30? What is phi1 to the power of 60? Before you answer that, everybody,
Gets smaller and smaller.
Yeah, 0.9, any number less than 1. If you if you square that number, 0.9 squared is less than 0.9. You all agree with me?
Yes.
0.9 to the power of 3 is even smaller. 0.9 to the power of 10 is even smaller than 0.9. 0.9 to the power of 30, 0.9 to the power of 60 is even much smaller. So as this power goes up, the past 60 days, if we take 60, lag 60 days, lag 100 days, lag day by day, lag 60 days, lag 100 days, as n becomes large, okay, as n becomes large, what happens to this term? Look at the bottom of page 2. What happens to this term?
Gets 0.
It goes towards 0. All right, let me go back to you see? So this is page 2. I'm now back to the bottom of page 2. So where did we leave off? That the expected value of the process is equal to mu into all of this plus this last term. But because phi1 is less than 1 here, like 0.9. So phi1 to the power of n, where n is very large, phi1 to the power of n, this thing here will tend to 0, and 0 times this number. So all this stuff will disappear if we keep going back, okay? Therefore, the average value of the AR1 process is given by only this thing in the here, this one, because this one cancels out for large n. All right. So now on page, I'm now on page 3, okay? So, and so we're saying that because this tends to 0, therefore, the expected value of our AR1 process is given by this. Okay? Guys, if my AR1 process has 0 mean, yes?
Yes.
If this is 0, then the average value of the whole process will be equal to
0.
Roxolana, you see that magic?
Yes. Interesting.
If Lily doesn't talk to me now, I don't continue this class.
I got it.
No. I don't buy that, Lily. I mean, either I suck so much and you don't even bother with me, or I am just the best teacher on earth. And I know I'm not the best teacher on earth. So,
It's definitely the latter.
so okay, you have talked to me, so I can move on. Danny, you still here?
Yes, sir.
Okay. Hey, Min Lee, you still here, my buddy?
Yes, sir.
Okay, excellent. All right. I know the rest of you are here. I'm just calling 3 or 4 people for now.
Yep.
All right, so look. Now I want to do something from, all right, just to finish this. So let us rewrite E this in 3 above as here. So we remove the parentheses. Did somebody just chat me? Okay, so we remove the parentheses, okay? So up here, I remove the parentheses. I go back to, because I've gotten rid of that nasty term at the end. Now, let's see if let's remove this bracket and let's see what we have, okay? So here is mu plus, I'm sorry. So this one, mu times this is this, mu times this is this, and so on. So I remove the bracket, I have this. Now, again, I'm sorry to remind you guys of your nightmares from calculus, but I'm sure many of you remember this. Something called an infinite series in calculus, remember? Does anybody remember infinite series?
I think so.
Yes. So this is an infinite series that says that this first moment, the expected value of our daily returns is equal to some average plus some average times a constant term plus the same average times, so this one, I multiply it by this constant, phi1. This whole thing, I multiply it by the same constant, phi1. This whole thing, I multiply it by phi1 to get 3. This whole thing, I multiply it by phi1. So this is an infinite series that each expression is different from the previous one by the same constant term, phi1, okay? And if you have that, calculus tells us that this same average is the same as the first term, this one, divided by 1 minus that constant difference between them. Guys, what is the difference between the first and the second term? It's phi1, right?
Yes.
What is the difference between this term and this term? It's phi1. So if you have such an infinite series whose members are separated by a particular constant, then the average of that infinite series is given by the first term divided by 1 minus that constant that separates each term. So therefore, the average value, the first moment of an AR1 process with a 0 mean white noise is given by that, the AR constant, the constant of the AR process, divided by 1 minus the coefficient of the lag value of X. Now, everybody keep looking at this, okay? Keep looking at this equation, this one here. And let me go back to the textbook. Gosh. Ah, here. Everybody look at this term. You see that? The expected value of this process is equal to the first term divided by 1 minus phi1. Everybody see that, right?
Yes.
Okay. If this first term, the mean of the Ar1 process, if the mean of the Ar process is 0, okay, if this constant is 0, then this thing is 0. 0 divided by anything is 0. You see that? Okay.
Mhm.
So when we have an Ar1 process with this constant value, the mean of that process is given by the constant value divided by 1 minus the coefficient of this term. Okay, everybody? Yes?
Got it.
Okay. If you got it, then look at this. Can you see this, guys? Can you
Yes.
see? Okay. What for this Ar1 process? What is the constant term?
0.9.
No,
Oh, 0. Zero.
The constant is the 0. Okay. Therefore, the mean of the entire process will be 0. You see that, right? Because it is the constant term divided by 1 minus the coefficient of the lag variable. You understand?
Yes.
Yeah, and here the lag variable is 0.9. So.
Here, the lag variable is, no, the lag variable is xt minus 1. And
Oh, I see.
And its coefficient phi1 is 0.9.
Yes.
So this Ar1 series is equal to 0 plus 0.9 xt minus 1 plus the white noise. Because that first term, that first constant is 0, so the mean of this process is 0 divided by 1 minus 0.9. You see, that's why this is 0.
Oh, I understand. Okay.
Okay, and now let me just take this home. Okay, so this is like E of, I'm sorry, everybody just bear with me. Okay, E bracket x of t is equal to 0 plus 0.9 times x of t minus 1 plus w of t. Sorry, w of t. Please, guys, bear with me. I'm just trying to show you something here. Okay, if you look at the chart I just sent everybody, this is that Ar1 process. Okay, you're looking at it on the chart. What is its mean? Its mean is equal to 0 divided by 1 minus 0.9. See that on my chart?
Yep.
0 divided by 1 minus 0.9 is equal to 0. Okay? So for an AR1 process, the mean of the AR1 process is equal to the constant term divided by 1 minus the coefficient of the lagged variable. Okay, guys? All right. I was able to run through this. Okay. So I'll let you, before we finish, let me show you something now. Next class, after every discussion we'll have at the beginning, next class, I will show you that the variance, okay? Guys, I'll show you that the variance of an AR1 process is given by this expression, this one. Okay, I'll prove it. It takes a little while to prove, so I'll begin next class and probably end up on Tuesday. But guys, we shall go through the same process as we went through today. We write it, then we take we determine the variance, and there'll be xt minus 1 on the right-hand side. Then we shall substitute out xt minus 1 using xt minus 2, and then we shall after that we shall substitute, replace xt minus 2 with xt minus 3, and with the same recursive process, we shall arrive at an equation like this. Okay. Hold on, everybody. What time is it? Oh, it's 7:07 already. Gosh. This class, before I open my mouth, is over. All right. So next class, actually, this is what I'm going to do next class. Okay. Next class, I'll begin to show the autocovariance and autocorrelation process. I'll begin to determine for an AR1 process, what is the autocorrelation at lag 1? What is the autocorrelation at lag 2? What is the autocorrelation at lag 3? So I will go through that equation, but the variance will be autocorrelation and autocovariance at lag 0, yes? So the same, so I'll just derive the autocovariance formula for an AR1 process, and then when you plug in lag 0, it will be the variance, okay? All right, so that's what we shall do beginning next Thursday. Hold on, let me stop recording.
The recording has stopped.
Okay. Now, let me say this, everyone, before you leave, okay? The homework, this homework 1, I graded it very harshly. Okay, everybody listening to me? I graded it very harshly because I wanted to make a point for this class. Many of you were just, I mean, annoyingly careless, because you guys, I think something called senioritis has set in. Many of you will graduate either this May or whatever, and you are just almost brain dead. Or you're, I know, because I was a senior, and actually, I was a senior one time. And the day I defended my PhD dissertation, after defending my PhD thesis, if you ask me, what is your name? I was not able to say my name. That's how brain dead I was. I presented for like 2 hours in front of my committee, and those people, they just, they push my brain left and right. So after the day I finished officially my PhD by presenting my paper, if you had asked me, Professor, what's your name? I would not be able to answer. That's how brain. So I recognize that senioritis in many of you. So I graded you very harshly on this homework because simple instructions. I gave you, step 1, 2, up to 10 items for the homework. And at the end, I actually told everybody how I wanted your report to be. 1-word file, only answers. I don't want anything else. The other word file, I wanted the commands plus the results. When you type the command in R, it gives you the result. You type another command, it gives you the result. What did I say? Everybody copy that, put everything in the Word file. So I wanted 2 Word files. One of them with no R commands, no results, only answers to my question, all the questions I asked you. The other Word file would be the commands plus the results of the command only. But what was I seeing in this file with only, that's supposed to be only answers? I saw many of you putting your graphs here, no. And then the most frustrating is the last question, the JB test. What did I ask you? What is the null? What is the alternative? Half of you didn't even bother to write me the null and the alternative. It's just like, oh, I reject, or oh, I failed to reject. Huh? All the time I took spelling everything else out, I just felt like an idiot. So I graded you very harshly. Don't be surprised. And get this, everybody that did not submit by deadline on Saturday, every one of you got 0 for this homework. Because what did you do? You sent me your homework to my email address. You know what I did? I just put it in the trash.
Professor?
Hey, I don't want to hear. That will fix you. So homework 2, if I give you deadline 11:59 on a given day, if you miss that deadline, you get a 0. Okay, of course, a couple of you, I won't get a 0 because you were sick. That's okay. I respect that. Okay. So, but for the rest of you, you just it's Onochi afterwards. Onochi is going to accept whatever I give him. Son of a bitch, Nigerian. Everybody that submitted to me directly to my email or to the TA Chan, you all get 0s in this homework. And it stays 0s, it's going to stay 0 unless for the rest of the semester you submit on time. Then at the end of the semester, I might reconsider. Hey, Roxolana, what did I say? Did I say I will for sure reconsider? What did I say?
No, you said you might reconsider.
I might. Thank you, Nikhil. Maybe. So Nikhil, you are my witness. Where's my friend Lily?
Here, of course.
Okay, so you are my witness, right?
You got it.
Okay, so I said I may. That doesn't mean I will. But the first condition is all of you that submitted, all of you that didn't submit on time, you get a 0 for now. And then I have my eyes on all of you for the rest of the semester. If you miss one homework by half a minute, then this 0 in the first assignment counts for sure. The highest score was 95 out of 100, which is 9.5 out of 10.
Is there a curve?
I'm not curving. I'm just so pissed off with this class.
Oh, I'm sorry.
No, because like 1/3 of the class or whatever didn't submit by 11:59, and then somebody even submitted yesterday. I had to drink something to calm myself down. And that person, oh, professor, here's my homework, professor. On Monday, it's like 3 days or 2 days after Monday night, which is essentially 3 days after it was due. Is there a homework key like what you actually wanted as an example? No, there's a key, yes. But I want to discuss the key with everybody, okay? So I plan to do that the first half of class on Thursday. Who asked me that question about the key? Thank you. Okay, because that's what I want to do. So on Thursday, I will begin class. That's Mayor Sylvie, thank you. On Thursday, I will begin class with a discussion of what I expected. Okay? So that
like
you
what
will,
you expected and all the right coding and all the right answers given and
everything.
Okay, perfect.
Because from now on, I don't want there to be a question about what did I expect. Okay?
Okay, perfect.
All right. But many of you guys, many of you in this class, you did it well. And I congratulate you. You did it perfectly well. Okay. I was just being nitpicky because I was already annoyed with the whole class because they didn't so. So I really graded this harshly. If you make one simple mistake, I just took off points. Okay, so that's why there's nobody that got 100. But I will explain more on Thursday for you, okay? I mean, there was some people made 2, some people made 3, some people made 5, some people made, and I'm sure those people that made 2, 3, and 5, and 6, they, of course, when they submitted, I'm going to get the whole point. No, you didn't. Okay.
Wait, so you're saying the 1, 3, 5, like those kind of grades, is the code graded anything, like by actually getting the code right? Like, let's say the answers were not
Yes,
all
yes,
right.
yes. I mean,
Get it.
what is the time now? It's 7:16. In exactly 14 minutes.